Okay, in this presentation we're going to look at a statistics with R presentation. This is an introduction to R for actuarial students. This corresponds to the CS1B curriculum that comprises Introduction to R programming, fundamentals of statistical analysis such as hypothesis testing, and probability distributions. This particular example we are looking at random number generation of the exponential distribution. This is question 2 of this playlist. Just as a quick remark, not really relevant in this particular presentation, but the syllabus works on the basis of base R almost exclusively, unless you're told specifically to load a particular program. So if you're wondering if there's no tidyverse or ggplot in this, I put them in just as additional comments. They're not part of the curriculum, and that's why they're not featured so heavily. So when you execute any R code in this question, make sure you run the entire R script, including the line set.seed 1234 at the start. Okay, just pick a seed and stick with it the whole way through, just to make sure that the answers are consistent. You might be told to use a particular seed. Quite often in exam questions, it might be the year, like 2021 or 22 or 23, and so on. So use the command set.seed 1234 to initialize the random number generator. So there you are, you're told what to do. So let's look at the first 4 of these questions. Generate a sample of size n equals 180 from an exponential distribution with rate parameter lambda equal to 5. Calculate the sample median of the sample in part 1, that's question 2. Question 3 is calculate the median of the exponential distribution with lambda equal to 5. Now that is to say the population median, okay? So the analytical solution to what the median should be when lambda is equal to 5, and comment on your results in part 2 and 3. So just go with parts 1 to 4 there, and we'll come to the other ones shortly. So first off, we set up our seed, set seed 1234. We specify lambda, the rate parameter for the exponential distribution. We're going to permanently keep that as 5. And the sample size is going to be consistently 180 throughout the question. So we'll just stick with that. So if we're writing a big long R program, we would have these set up at the start rather than having to sort of pick our way through the whole R script just to sort of change it one by one. So exercise 1, generate a sample of n equals 180 from the exponential distribution with rate parameter lambda equal to 5. So the command here is REXP. R is for random numbers. Okay, EXP is to specify the probability distribution. The sample size is something we specified in the previous slide, so that's stored in memory. Okay, so it just knows it's automatically 180. And lambda, likewise, is the rate parameter that we have set here as 5. Okay, so they get stored in an object called x, which is numeric vector. And let's just quickly look at them there to sort of see what they look like. The first 6 of them there, just to make sure that everything's okay. Looks pretty good there. We can change the precision, but we don't really need those decimal places. But by the same token, there's nothing really important about it or urgent about it, so we'll just leave it as is. Now, something that's actually interesting, and just as sort of an additional comment, that it's well worth actually sort of seeing if you can try out inverse transform sampling. Now, the exponential distribution is a straightforward example, and this is how you might go about doing the same problem, just with a different piece of code. Okay, and okay, so we'll leave that there. Just as sort of a quick remark, how would you go about that if you were asked to do it from first principles? The first question is calculate the sample median of the sample in part 1. So we just actually specify the median of x there, like that. We can save it as m and just print out what m is. It is 0.1306305. Okay, 1.306, let's say. Okay, now this is the analytical solution. This is exercise 3. Okay, so what would it be for the population? Okay, the population median. Okay, now this is not based on the sample. This is an analytical result. Okay, so we get the quantile of the exponential distribution that corresponds to 50%, 0.5, when the rate parameter is lambda equals 5. Okay, so that's the code there. Now that's an analytical solution. That's not based on the sample. There's no mention of x there at all. Okay, this is the population median, so to speak. MQ. So that's it there, 0.1386294. Okay. Now they're close enough. Comment on your results in part 2 and 3. The sample median in part 2 is an estimator for the true median in part 3 based on the sample in part 1. Now, in general, the results in part 2 and 3 should be fairly close to each other, and if you're to rerun the analysis again and again, the medians should be consistently, the sample medians should be consistently in the region of 0.1386. So the difference is a sampling fluctuation between 0.1306 and 0.1386. That's a sampling fluctuation. Right, the maximum likelihood estimator for lambda is given by lambda equals 1 over x, where x is the sample mean. Estimate the parameter lambda using the maximum likelihood estimate and the sample in part 1. So for the parameter of an exponential distribution, the MLE is the inverse of the mean. So essentially what we have to do there is just calculate the inverse of the mean. 1 over the mean, that's our value there, our likelihood MLE estimate, okay, and that is 5.25. Now essentially what are we comparing that to? That is our, based on the sample estimate, that's our sample estimate, that is rate parameter of 5. That's an estimate for 5, okay, based on the sample. Okay. Generate another sample of size 180 from an exponential distribution with rate parameter lambda equal 5, and estimate the parameter lambda using the maximum likelihood estimator and the new sample size. So essentially what we're going to do is generate a new sample, okay, and do the same thing again. Okay, so x2 is just the second sample we generate. It should be very close in terms of mean and median to the first sample, and here the mean is, or the MLE is 4.89, okay, and again that's close enough to 5. Okay, and the differences between the MLEs and the true mean, or the true rate parameter, is the theoretical one, is simply down to sampling fluctuation. So the estimates are both close to the true value, lambda equals 5, that should say, but are not identical. The actual value of the estimator is a random variable, and the estimate depends on the estimated value depends on the sample size. Again, that's related to sampling fluctuation. Okay, leave it there.